Welcome to this explainer. Okay, if you've ever stared blankly at a spreadsheet, desperately trying to remember if it's an HLOOKUP or a VLOOKUP you need, well, you're definitely not alone. Today, we are unpacking a really fascinating piece of AI news that's solving a massive headache in spreadsheet automation. We're talking about a brand new framework called FormulaSPIN, and it is literally conquering the AI data saturation problem. If you're building natural language to code models, you're absolutely going to want to pay close attention to how this iteratively improves generation without needing any extra human annotations.
So here's our roadmap for today. We'll start with the data saturation wall, then enter FormulaSP, see how it fixes contradictory gradients, look at its adaptive curriculum, check out the benchmark results, and wrap up with next steps for developers. Let's dive in. Section 1, the data saturation wall. We are fundamentally hitting the limits of human-labeled data.
Which brings us to a really critical question. What actually happens when an AI just runs out of human data to learn from? I mean, hundreds of millions of people use spreadsheets every single day, yet writing complex formulas is still a super high-friction task. We want AI to do it for us, right? But training these sophisticated models requires supervised data, and the reality is we're simply running out of it.
Think of data saturation kind of like maxing out your level in a video game, but only using the tutorial quests. Once you burn through those static, human-annotated examples, throwing more computing power at the model just gives you diminishing returns. The main bottleneck here isn't the model's actual capacity, it's these static data limits. We desperately need a way for the AI to get better without humans having to painstakingly label more and more examples. Section 2, enter FormulaSPIN, which frames training as a two-player game for iterative self-improvement. This is a complete paradigm shift. It's an execution-aware self-play framework recently accepted as an ACL 2026 oral presentation by author Sai Ji. Instead of begging humans for more preference data, FormulaSPIN reframes training as a continuous two-player game. The current AI model basically competes against its own previous checkpoint. It's exactly like racing against your own ghost data in Mario Kart. Through this loop, it gets better automatically, shattering that supervised fine-tuning ceiling without a single new human annotation. The secret sauce here, it's all about shifting the training signal from syntactic approximation, does the code just look like the answer key, to semantic correctness. In this game, the referee isn't a human checking syntax. The referee is this ruthless, deterministic execution engine that just gives a simple binary pass or fail. Did the formula execute successfully? Yes or no. The whole focus shifts entirely to whether the formula actually works in a real environment. Section 3, fixing contradictory gradients and overcoming the flaws of FormulaSPIN. Now you might be thinking, hey, if self-play is so great, why not just use standard self-play iterative fine-tuning, FormulaSPIN, to do this? Well, the fatal flaw with FormulaSPIN for coding tasks is that it's just way too rigid. It penalizes any output that doesn't strictly match the reference formula character for character. That creates what developers call contradictory gradients, which totally destabilizes training by punishing perfectly valid formulas. FormulaSPIN solves this with a clever semantic-level voting mechanism called execvote, which groups execution-equivalent formulas together before applying reward signals. Okay, picture this. A model generates a formula that reads equals A1 plus A2 plus A3 plus A4 plus A5, but the reference key says equals SUM A1 to A5. Both formulas do the exact same logical thing, right? They give you the identical result. Actually, scratch that, FormulaSPIN would literally punish the model for the first one. By clustering these variants at the semantic level with execvote, FormulaSPIN makes sure the model learns to prefer correct behavior rather than blindly memorizing one specific syntax. Section 4, adaptive curriculum. It uses a very deliberate two-phase training approach. To keep the model from getting overwhelmed, they don't just throw it into the deep end. Phase 1 is purely about survival. Semantic correctness. Does the formula run without throwing an error? It uses execution feedback as a hard filter to toss out broken code. Then, once it stops generating errors, it graduates to Phase 2, stylistic refinement. This is where it learns to write clean, idiomatic code matching the reference syntax, ensuring stable learning without punishing those valid variants we just talked about. Section 5, benchmark results. Let's prove the actual power of this execution feedback. Does it actually work better in the real world? The answer is a massive yes. On the NL2 formula benchmark, FormulaSPIN hit an 87.1% execution accuracy. To put that into perspective, that matches models trained with heavy, expensive human preference annotations, and even outperforms frontier proprietary models. It proves beyond a doubt that binary executability is a much stronger training signal than static human labels. The data here is super telling. We've seen exact string match of about 75%, but an execution accuracy of over 87%. This proves a really vital point for us. Exact match is nice for debugging, sure, but getting a spreadsheet formula that actually works without throwing an error, that is what users actually care about for their day-to-day productivity. Section 6. Next steps for developers. Here's how you can apply FormulaSPIN to your own pipelines. For the data scientists and AI researchers watching, the official open source implementation is already up in the early development Xtronzy FormulaSPIN repo on GitHub. You can apply this today. First, swap out brittle string matching rewards for sandboxed binary execution feedback. Second, use xvote for semantic voting to kill those contradictory gradients. Third, pin your base model versions and snapshot checkpoints frequently, because self-play will amplify drift. Fourth, tune that adaptive curriculum gradually. And finally, always validate your sandbox against edge cases like circular references or complex arrays. So as we wrap up this explainer, I want to leave you with this to ponder. If binary execution can successfully replace expensive human data for spreadsheets, what other executable domains is self-play going to conquer next? I mean, anything with a deterministic environment, SQL, regex, shell scripts, could theoretically use this exact same self-play loop. It's a real game changer for how we train specialized coding models across the board. Thanks for joining me today, and definitely keep experimenting.